Basaltic Andesites of the Oregon High Cascades and Deep Oakland, a geological human braid. Welcome to the GSOC Geology Hour, our monthly gathering of geology enthusiasts, brought to you by the Geological Society of the Oregon Country, with support from the Beverly Vogt PSU Scholarship Fund and the Portland State Department of Geology. So hi, everybody. My name's Alyssa Smith. I am one of your co-hosts today with Carrie Gordon. And then our primary speaker today is going to be Andrew Alden. And today I'm going to be presenting a little bit of my kind of just a really broad overview of my research. So this is a picture of a portion of my field area out by Davis Lake in just south of Bachelor. But yeah, today I'm going to be presenting on basaltic andesites, the dominant lava type of the central to northern Oregon High Cascades. Part of this was funded by the Bev Vogt Scholarship Fund, and I'm eternally grateful for that, and also some of my other sponsors thus far. So to get us all started here, I want to start by getting everybody up to speed with just some very broad definitions. So simply put, volcanic rocks can have a lot of different compositions, and I'm broadly simplifying these classifications based on their silica content. So mafic rocks are going to be basalts and basaltic andesites up to about 57% weight silica. Intermediate rocks and felsic rocks are going to be higher silica than that, so andesites, dacite, and rhyolites. So the composition of lavas are controlled by numerous magmatic processes. That's why we have kind of a spectrum, and I like to include that here because we as scientists like to draw much more definite lines than Mother Nature does. So everything's kind of a continuum. But my focus is going to be specifically on those mafic rocks, so basalts and basaltic andesites, but very specifically, I'm looking at basaltic andesites. So as far as my field area goes, it's a portion of the Oregon Central High Cascades is how I'm abbreviating it. It's really northern to central, but that's a lot of words. So this is a period of the overall Cascade arc, the High Cascades being from about 8 million years up to the present. And the Central Oregon High Cascades here is unique even within the Cascade range because of the just kind of outrageously high vent density in this area, lots of very small individual volcanoes. And also there's the highest proportion of mafic lavas within the Cascade arc. So of this, basaltic andesites have been the dominant lava type produced in the Oregon CHC for at least the past 7 million years. So my study area aligns with this diagram here, and there's my pointer, extending roughly from Mount Hood in the north to all the way down to the city of Crescent in the south. Huge area. And on this map, which I took from the Hildreth compilation of Quaternary volcanism in the Cascade Magmatic Arc, all of these individual points are volcanic vents, and all of the dot shapes, I know this is very small, all of the dots are going to be mafic vents, and the pluses are going to be other compositions, intermediate and felsic. So you can see there's quite a bit of, it's predominantly mafic here. So I'm going to touch on a little chemistry, but I'm going to be doing mostly a very broad overview today. So I want to take a little step back and use a kind of an analogy. So one of the many questions we can ask about a lava is how it was generated or what chemical geological processes kind of were responsible for their chemical signatures. So mantle melt, if we were to have a situation where we had melt generated in the mantle and that goes through the crust without any sort of impedance or interference, we'd be left with what we would call a primitive basalt. And this has a very definite definition, which I'm kind of glossing over. But essentially, we can think of its fingerprint kind of like this. So the lava itself is going to be very close to that mantle composition, which is supposed to be that green print there. And there will be a little offset just due to how much melt you're generating, what minerals are present in the mantle, things like that. But it's going to be the closest, essentially, those primitive basalts are going to be the closest that we get to the composition of the mantle, which, since we can't get down there to study it ourselves, we kind of rely on these lavas. So basaltic andesites can still be relatively primitive, with like little overprinting from stuff that happens in the crust, but a lot of the time there's still going to be overprinting from various geologic and magmatic processes. So there have been quite a few studies on primitive Cascades lavas. Not all of these are in my area specifically, but the findings kind of hold true throughout. So there are at least 5 mafic magma groupings that have been proposed, kind of depending on which study you're looking at. And these are based on major and trace element concentrations. So the Lehman et al. Study grouped all of these into just 2 like bigger, broader groups, which would be the intraplate type lavas, which are going to be comparable to mid-ocean ridge basalts, that's this LKT, low potassium tholeiites, and ocean island basalt-like lavas, which have the very creative title of OIB, ocean island basalt-like. And that group is inferred to be decompression melts, so from extension in this area, with little to no subduction signature, which is, important to consider in the fact that this is a volcanic arc. And then there is the calcalcalic group, which is going to contain the more typical arc-like lavas. So that's CABs and HKCA. So that's calc-alkaline basalts and high potassium calc-alkaline basalts. Shoshonites and absarochites, which essentially are just very, very high potassium basalts. These are pretty unique and not very common, but still worth mentioning. And then basaltic andesites have been just kind of group lumped into this. So these are inferred to be shallow melts triggered by the rising of those intraplate type lavas. And these calcalcalic lavas, are going to be those that have subduction signatures. So the diversity within these groups and between the 2 groups are largely a function of volcanic production rate, so how much volcanism is happening, the depth and the amount of mantle that you're melting, the composition of that mantle source in general, because it can vary from location to location, and also just heat flow in the system. So going back to our fingerprint analogy, in most cases, when you evolve a magma from like a primitive basalt to anything else, the chemistry can start to get really messy. The journey from the mantle to the surface is pretty complex, and basically anything that can happen to a magma in that whole process can overprint some of the chemistry. So some of these processes that can occur can be things like crystal fractionation, where you've got magma that starts to cool and minerals crystallize out, and therefore that changes the composition of the leftover magma. You can have crustal contamination. So anytime either that melt is passing through rock or sitting and stalling, you can incorporate some amount of that, which also is going to change the chemistry. And magma mixing. So you can have just some of another magma body mix in, and that also changes the composition. So we can model a lot of these processes at least as best we can, to try and quantify how much of these processes have occurred since that original generation of melt. And also, it looks really messy in my illustration here. And I mean, it still kind of is. But we have to remember, going from basalt to basaltic andesite is not going to be nearly as problematic as once you start to move further and further away from a primary melt. So ideally, it's a doable thing, but that's kind of what I'm going to be looking at. So what have others done with basaltic andesites? I've already mentioned basaltic andesites in this area are more abundant than true basalts, but they've been subject to notably fewer studies. So there's just been disproportionately less work done on basaltic andesites. Some of the early studies on basaltic andesites, the few that have been done, put these basaltic andesites into 2 general categories, very, very broad, based on some chemical generalities. So there's the North Sister type, which is going to have low potassium and low concentrations of things like large ion lithophile elements and rare earth elements. And then the Mount Washington type is going to have higher of those things. That's about as specific as it gets. And probably the most notable thing these studies, even though not all of them have kind of come to the same consensus about how individual centers were producing lavas, is that there's not a straightforward explanation which ties basaltic andesite types to the primitive basalts that have been grouped. So it's not really understood why. Either there's got to be some sort of process that's overprinting those signatures, which in sometimes I'm glossing over something big, but it's kind of hard to explain that in some situations based on some chemical markers. Or it may be that whatever melts that produce these basaltic andesites are never erupted as basalts, and they just kind of go to basaltic andesites. And so that's a big question. But also, it's not explained why basaltic andesites are so much more voluminous than basalts, or even why is it that we're not getting as many andesites. So these are just some big outstanding questions that just means that I have some work to do, which is great. They just left things for me. So essentially what I'm going to be doing is I'm going to be looking at the distribution and compositions of mafic lavas in the Quaternary Central High Cascades. I'm going to be developing a chemical classification system for Central High Cascade basaltic andesites. And then I can use those classifications to propose models that are going to explain how we make these different types of basaltic andesites based on their chemistry. So what that comes down to is I've been doing a lot of field work. So I've done 2 seasons already, and I'm going to be beginning again in June. And here's some of the many pictures I've taken from my field area. But essentially what I've been doing is using a large amount of published and unpublished geochemical data and kind of putting those over geologic maps to figure out what areas have not been sampled. So what's also been really helpful in that process is using publicly available LiDAR data, which not only can kind of show me what I'm getting into when I'm about to go out and do my little hiking thing, but also what's been really, really successful for me is using those LiDAR data to figure out where there's likely to be actual outcrops I can sample. So I'm pretty proud of myself for doing this. I don't think it's anything new, but nobody told me about it. So I target my sample locations on that. And the great thing about this is I have made it a point to prioritize bringing as many undergraduates from the PSU geology department with me, so they're able to get field experience that they can put on their resume. And this has been wildly successful. And I've also been able to provide references for people. And what's even cooler than that is all the people I've provided references for have got the opportunities they were applying for, which is really, really awesome. And that's what we want. So the next step is going to be lab work. What I've done so far is bulk rock geochemical data, which has pretty pictures. So essentially, I take the samples I collect in the field. They'll look something like this, or they look a lot of different ways. And I crush those up and put them in little to-go ranch containers. I forget what they're called. And then take them to Washington State University's geoanalytical lab. And then they are ground down into a very fine powder and mixed with a fluxing agent, which makes it so they will melt easier, because the next step is turning them back into the lava from whence they came, and which is really, really neat. You put them in the oven at like almost 1,000 degrees. I can't remember if it's Fahrenheit or centigrade, but at that point, does it really matter? And then you get a really neat little glass bead out of it. And we can't just leave things as they are, because we need to take some of the powder back now that it's been homogenized. So we have to crush it again. And yes, that's the same exact picture, because I only took one of that process. We remove a bit of that powder now that everything's homogenized. There's no like minerals or anything in there. It's just powder. And take that out for laser or ICP-MS, inductively coupled plasma mass spectrometry, not lasers. And then melt them again, and there's me with my lavas that are cooling, and it's really, really neat. And then from there, the refused glass is used for X-ray fluorescence. So we get another set of data from that, and ta-da, then I get chemistry. And so I'm just going to gloss over this. The data analysis is not the most fun for pictures, but a few things I'm doing is some spatial analysis. So using available map data and geochemical data, and just kind of trying to, figure out some spatial components. And also, it's been compiling geochemical data that it will eventually make its way into a publicly available geochemical database for mafic lavas of this area, and then geochemical data analysis, which I'm just glossing over. And I usually do my work at a coffee shop, so there's a copy there. So the next steps, I'm aiming to complete a significant portion of my fieldwork this season. This area over here, south of Mount Bachelor, is the area where there's been the least samples collected. So the red and yellow symbols are things I've collected. The blue is what other people have collected. And the green are places I'm hoping to finish this summer, which looks like a lot, and it is, but that's my job. So after this, I'll have more data collection. Going to incorporate a few different types of data and just continue my analysis, because more data means more concrete findings, and just a lot of this is front loaded with I just need to get a lot of data before I can say too much that's very exciting. And then ideally I'll finish my graduate in 2026, which seems so far away, but it's not. And in summary, basaltic andesites are the dominant lava type within the contemporary Central High Cascades. There's been a notable chemical disconnect from regional basalt types, and so my research focus is going to be characterizing basaltic andesites and proposing models for basaltic andesite genesis. And with that, I will thank you all.
Oh, Alyssa, that was absolutely delightful. And I know you'll catch up on the while I'm chatting here, folks. If you have some questions, please drop them in. And I do have a question for Alyssa. But
Sure.
first off, Carol had an awesome, she said, great magma description, Alyssa. Would love to get this show for an article on the website. And I
Sure.
totally agree, because you've done a wonderful job explaining. So I
Thank
do
you.
have a couple comments here. So a lot of us think about wildfires as being not helpful. However, for geologists in the field, if you didn't notice, Alyssa was able to see at a distance and see those points that she was going to be aiming at for her hikes. So sometimes wildfires are our friend from a geologic mapping standpoint.
Yes, there have not been fires that have cleaned out the areas I've been needing, but there have been fires that have cleaned me out of doing my work. So there was one this last summer that my assistants and I looked out and we're like, what a beautiful view of the Cascades. And then we went down the road, came back, and this was our view. And I saw it. I'm a canary in a coal mine for smoke. I could smell it, and I was like, nah. And then we could see this plume coming out from behind the North Sister. And within about an hour, this is what we were looking at.
Yep.
So it
Yeah.
was early this year.
Yeah. That's why you need to be very careful and be conscious.
Oh,
So
yeah.
one of the things that I am back with LiDAR. Air photo interp was our precursor to LiDAR, and air photo looking through stereoscopes also is a really good way of finding your points. But LiDAR is a cool technology, and I have to admit it's eye candy. So I do have a question for you with respect to the basaltic andesite.
Uh-huh.
So I know these are young basaltic andesites.
Yes.
So have you looked at some of the basaltic andesites or considered the genesis of some of the basaltic andesites in the Ochiko Mountains that are basically Clarno age?
I have not, because this is just such a gigantic project on its own, that I'm like, I have to get this one down first. But, I don't know what my next project will be. I love basaltic andesites. I think they're so beautiful. and they're just so glossed over, and that might be something I could look into in the future.
The reason I bring it up is because I worked with a lot from mineral material use, and the platy andesites, basaltic andesites, were quite useful as building stone. In addition to Paul, see another building stone opportunity here. So thank you very much, and
Yes,
I will let you introduce Andrew. And
sure.
I don't see. Oh no, there is one question. Paul Shia had a question. What is the role of the subducting plate on the chemical composition of the Cascade lava?
See, that is such an interesting question. Because for so long it was kind of anticipated that, yeah, these are just subduction created lavas because we've still got convergence and all of that. And actually, what it's looking like is that a lot of the subduction signatures in these young lavas are actually relict signatures. So it's from mantle that was previously altered by subduction, but currently the plate under this part of the Cascade range is really, really deep. And so it's not quite expected that it's contemporary subduction that's doing this chemical alteration, but that it's from this long-standing metasomatism of the mantle, because a lot of this is extension dominated. That was what that transition was at about 7 million years, went from convergence, like convergence since 40 MA up until, like I said, about 8 to 7 MA, when it started to be, you have more of that extension going on. And that's what's facilitating the generation of melt, and then also allowing these lavas to rise. So it's a really complex question, but it explains why we have those intraplate looking magmas. That why would you have those in just a compressional arc setting? Is it's got to be the extension. So it's absolutely fascinating. And that's something that varies a lot through the range too, depending on how much of the current drivers are still compressional and how much of it's extensional. So it's super neat.
A lot of questions to be answered. Well,
Oh yeah.
so I'll let you introduce Andrew.
Sure. Yeah, I'm going to be introducing our speaker, Andrew, who is going to be talking about the so Deep Oakland, the geological human braid, and my brain blanked adding in more. So if you'd like to add more, I would love to hear it. Sorry, I was in presentation mode.
Hi, folks. It's it's a real treat to be part of your meetings. It's lovely to see such an active geological society. There's no guarantee that any of them will last. You know, um, my own local geological society was founded in 1944, and it's had its ups and downs. And anyway, it's nice to see a real vigorous geological society. Let me share my screen. Deep Oakland, a geological human braid. When I moved to Oakland, 1989, it was 2 weeks before the Loma Prieta earthquake really awakened me to the reality of the Bay Area, where I'd lived for 50 years now. And as I explored it, I explored the city. I had I love the city. I love the city of Oakland. It's a very cool place. And I also discovered it's really exceptional in its geology. Am I have the video. Okay, thank you. Anyway, but thinking about Portland, I've been to Portland quite a few times, and they are both cool cities, and they have a lot of similarities. For one thing, they're both frontier cities. They started with the westward expansion, and they were in favorable places. You know, the geography favored them for one reason or another. They have a variety of topography in them. They're just interesting places, picturesque places to live in. They both have volcanic heritage. Maybe that's not as well known in Oakland's case as it is in Portland, but I'm going to tell you all about that. Both tectonically active settings, I guess I don't need to discuss that. They both have glacial features from the ice ages. And I didn't know that about Oakland either, although we all know that about Portland and the whole Pacific Northwest. They're both rich in resources, geological resources, from timber to water, building stone, and of course, agricultural soil. And another thing is they're not really in North America. And what I mean by that is, well, we all know about Portlandia, and it's a peculiar place. And Oaklandia is also a peculiar place. Oaklandia sits on the Sierra Nevada microplate. It's not really part of North America. And Portland is part of Silesia, which is an old oceanic plateau that docked against North America back in the Eocene and has been sitting there twisting and turning ever since. Portland is a big place, and this kind of shows the variety of terrain and topography. Now, for geology, I have to apologize for this. The state geologic map is not organized for presentations. And it kind of looks like there's not much going on here, but of course there is. All sorts of generations of lavas and glacial stuff going on. Here's Oakland. This is the same scale. Oakland is a much smaller city. And this is its geology. It's beautiful. I'm lucky, and Oakland is lucky that we had a USGS map devoted to the East Bay, the Oakland East Bay area. That was published in the year 2000. And in the book, I make the claim that Oakland has more kinds of rocks than any other city in America. By which I mean, if you set out to a grade school, or you want to make a rock collection of shale and sandstone and basalt and so on, you would get more rock types in Oakland than any other city in America. Now, that's a pretty bold claim. So I'm going to show you some of them. But let's talk, I'm going to summarize all of Oakland's geology in 2 sentences. One about the bedrock. And this is in condensed geological language. I expect you to digest it instantly as you read it. It's a subduction regime in 3 parts: accretionary wedge, an ophiolite, and a foreland basin. And then it's got a bunch of succeeding tertiary foreland sediments there after the subduction part. And the whole thing is dissected by faulting, by eastward dextral transpression. And I will start with that last sentence. This is that geologic map turned sideways, and the big feature you see between the sediments in their traditional map colors and the bedrock in their traditional map colors is the Hayward Fault. Hayward Fault defines Oakland's landscape. It has built and it maintains Oakland's landscape, and it's a right lateral transcurrent fault, the kind I don't think you have in Portland. That's the main thing there, and it's there's transpression across it. There's a little bit, about 1 in 10. It moves at around 10 millimeters a year sideways, and it compresses about 1 millimeter transverse in transpression. And so that pushes up the hills on the inland side, and the hills in turn way down on the San Francisco Bay block and push it down. And that's in a nutshell, how the Bay Area works. And it also means earthquakes. The last big earthquake ruptured the ground on the Hayward Fault was in 1868. It was on the 21st of October. And it was called the Great San Francisco Earthquake for the next roughly 30 years. And Oakland at the time, its tallest building had just been built. It was a 3-story brick and iron building called the Wilcox Block. At this time, the Transcontinental Railroad was coming through. It was going to end in Oakland, and Oakland was ready for a huge business boom. And so this building was built, and it survived the quake in beautiful shape, as the papers report the next day. It is well braced with iron, and the building is still there today. The other thing that's very cool about the Hayward Fault is that it's a creeping fault. The rocks deep down are under hard compression. They are gathering frictional energy ready for the next big earthquake, which can happen anytime, even as I'm speaking to you. But the shallow layers where the pressure is less are free to move, and that's why we get surface creep. And this is a spot I keep visiting every few years. And you can see this little fiduciary saw cut that someone left many years ago, and it keeps getting farther and farther apart. Now the actual creep is a wider zone than this single crack, but it's just a fun thing. And if I'm about anything, I'm about have fun with the Hayward Fault and make friends with the Hayward Fault, because someday it is going to turn on us. And then the second sentence about Oakland's geology is about its landscape. And that's where I'm going to start, getting into more detail. This is the last just million years, just the last tick of the clock in geologic time. And it's a combination of quaternary orbital cyclicity, that is ice ages, and the tectonic action that I've just been describing to you. The Hayward Fault in this view runs right through this ridge and right past that, where the hills leave off. And you can see the lowlands and the highlands, and that's Oakland in a nutshell. So this is a cool graph I made for myself about a year ago. I'm so excited. I've been sharing it with every audience since. This is all the streams that drain Oakland. And there's the hilltop. This is the ridge line to help you visualize the drainage pattern. This is in the hinterland, and it's governed by a whole different set of things. And then on this side of the divide, it's your ordinary mountain front drainage. And then this thing in the middle, that's the Hayward Fault, and you can just see what it's doing dynamically as each side of the fault moves to the right with respect to its counterpart. It is warping all these streams, and as they move along, I wish I could make a movie of this. You'll see the headwaters of a stream. They'll be switching between downstream sections. So it's there's this whole intricate history of Oakland's streams that needs to be ciphered out. Maybe I'll do that over the rest of my lifetime here. And I want to point out what happens to this block of bedrock. It's kind of unique in the East Bay in being on the other side of the Hayward Fault. If you run the fault back a million years, it ends up over here. And it's opposite this big body of Jurassic gabbro, which is very solid, a resistant rock type. And my hypothesis, which I expound throughout the first 6 chapters of Deep Oakland, is that when these two immovable objects were brought together by the irresistible force, they were both forced upward. We've known for 100 years that this is an uplifted block. The same rocks here are present everywhere else down below, several hundred meters, covered in young sediment. But this got bumped up, and this orange envelope around it is the mantle of ancient gravel, of mid-Pleistocene gravel that was originally on top of it. So I call that And this is a graph showing all that. I call that the hip check hypothesis, that the body got hip checked as they try to pass each other. And I'm going to talk about two pieces of evidence that fit with that. And the first one is about Saucil Creek. Saucil Creek is kind of cool. It cuts right through this block. In other words, there's a water gap there, right? But it's not much of a stream. This is it, after a winter rainfall, there's nothing much going on here. It's not very, you don't hear boulders rolling or doing any work, And yet somehow or other, there's this big canyon cut right through the block. You were talking about LiDAR earlier. This is LiDAR imagery, and it's just such a wonderful thing. And the whole United States is covered with LiDAR image of this quality. You can explore your region from your desktop. So anyway, these are the headwater tributary streams, and together they are renamed Saucil Creek, which runs down to the bay in a straight line. Now, as I told you, this is not only temporary arrangement. At some point, this stream, this canyon, this creek was down there somewhere. This canyon, Diamond Canyon. It's a classic water gap, and I argue that it was cut at the same time this block got uplifted. It was being uplifted, and the stream there, San Leandro Creek, which is a much stronger stream than Saucil Creek, cut the canyon then. So it's a almost classic water gap. It's a tectonically beheaded stream valley water gap with an Oakland style twist. And then here's the other corollary. This drainage, it drains the block itself. It does not drain the high ridge. It has not been disturbed the same way that these other drainages have been. And so, yeah, this drainage on this side, the San Leandro Creek drainage, this is San Leandro Creek here, great big creek that cut Diamond Canyon. It has a nice, well-formed drainage pattern down here. This has its own miniature dendritic pattern, a compact network shaped like the sketch of a tumbleweed. I didn't need to use the word dendritic, And they come together at Lake Merritt. Lake Merritt is this little wonderful water feature down here. This is Lake Merritt. Lake Merritt is Oakland's jewel. If you ever visit Oakland, and if you ever have visited Oakland, you just have to visit it. It's a world-class attraction. And I have explained why it's here in my book. And it's about the ice ages. This may be a familiar graph. It shows sea level, 200-meter range in sea level. And this is time going back about 800,000 years. And there's a real rhythm to this. This is the modern 100,000-year glacial cycle. It actually goes back 1,000,000 years, and then the rhythm changed before that. But when you talk about Oakland over the last 1,000,000 years, this has happened a good dozen times. So sea level has gone from zero, where it is today, down to 120, 130 meters. That's 400 feet. That's as tall as our tallest buildings. And so when you imagine the height of the ice age, the entire San Francisco Bay is empty. All the streams are cutting down to that new base level. And they're and so base level is oscillating. These streams are being cut down over and over every 100,000 years, and the sea comes back, and they all fill up again. They fill up both from the sea and from the hills. So they're all hidden. They're invisible, and as the bay itself keeps sinking, they're preserved underneath the ground, except in a few places like this catchment where the trench was especially deep, and this trench was especially deep, and so they remain in today's landscape. And so that's the story of Lake Merritt. The enhanced incision caused during the ice ages because of these repeated low base levels, 100 meters, 120 meters. And there's a couple other interesting quaternary landforms in Oakland, which I didn't really know about when I moved here. And I told you about this one. This is uplifted Pleistocene alluvium. Its age is not well constrained. There are no fossils in it. This is a quaternary landform. It's your classic alluvial fan from a major stream. In fact, it's so major you can see there's a reservoir that has dammed it, and that one underneath here, dammed in the 1870s. And then there are these. And then, of course, the Holocene landform, otherwise known as artificial fill, which has a very significant factor in Oakland's human and geologic history. So this is a fan. This is an alluvial fan, and I call this the fan in the book because it sort of has a fan shape, but it's not. It's a tectonic fan. And this is what it looks like. It's very well indurated. It's so indurated that when the backhoe cut this cellar hole, it broke through these clasts. You know, they're just broken because it holds them so firmly. So it's very cool stuff. It's sound foundation material. The other stuff is these pink fields. These are glacial terraces. This is one, and then there's also these dark blue ones, which I'll talk about later. The first one is the youngest. These are the youngest geological landforms in Oakland. And they're sand dunes, they're wind-blown sand dunes. They formed during the last glacial maximum. And the special significance of them is that this is where Oakland was founded, right there on that sand dune. And you can see it still exists as this beautiful level platform, maximum of 42 feet under City Hall. City Hall is that little tower there. And here along the shore, it's like 20 feet or so. And it is, as I said, it's Aeolian clay sand. There's a little clay in it, so it's very firm. And it's actually more like coarse silt than it is fine sand. And it's beautiful stuff. You know, I love it. Every time there's an excavation downtown, I go take pictures of it. And then the blue stuff is a terrace, a bay terrace. And it comes from the last interglacial, the last warm period, 125,000 years ago, or marine isotope stage 5E. And maybe you have some of this, in Portland. I actually don't know, and maybe one of you can tell me. And this is interesting stuff. I'll show it in two places. One is here in Lakeside Park, and then here in this residential area. So this is a nice terrace in Lakeside Park. It's a beautiful place. And this is it in this part of East Oakland, and you can see how level it is. It's like a billiard table. And so it was a very early town site in Oakland's human history. And it's topped with estuarine clay. Now, this is stuff, when the sea level was high, it was all marine clay. And then down underneath, it's this stuff, it's estuarine mud from the land side, from the hills carrying the stuff down. All these pebbles, and there's nothing in it larger than, little pebbles. And they're all stuff I recognize up on the hills. So it's just classic stuff to look at. So these two terraces, the young one was from the low stand and the older one was from the high stand. And for all I know, there's actually earlier ones in Oakland, but I have no way of knowing, And when you look at early Oakland, this is the first good map of Oakland. For one thing, you can see that Lake Merritt was actually a big old estuary. linked to another estuary, and this was a shipping channel that went all the way over here to this terrace and that terrace. And lo and behold, there were the first two towns founded here were there. Oakland was founded right here, and a little town called Brooklyn was founded there. Brooklyn actually came first because there was a Mexican rancho up here, and they used that as their landing. It was a nice navigable channel, especially at high tide. They could do their business. They could ship hides across the bay to a little village called Yerba Buena, where the English and American ships would trade for, lace goods and things like that the ranchos needed. In 1847, that little village of Yerba Buena renamed itself San Francisco, and they've been grabbing all the glory ever since. So, but before there were Europeans at all, there were the natives, the Ohlone tribes, and every talk I give, I acknowledge that everybody in Oakland, we owe it all to the Ohlones, and they're still here. They live here. They have a rising presence. They're actually regaining some of their lands in Oakland, but in their time, the lowlands were all meadows of various kinds and large oak groves on these terraces and wetlands, and they were all different resources at different times of year, all maintained by year-round use of fire. And it was another little thing they had there. They found a large deposit of ochre up in the hills here, and that is a very valuable trade good, ochre, because you can make body paint with it. You can use it for a mosquito repellent. You can use it as burial goods, decoration, and so on. And they had a monopoly on it because there was nothing like it for a good 100 miles around. So the Ohlones were rich. They were rich people. They had this ochre deposit. They traded it for arrowheads, finished arrowheads from the lava, from the obsidian up in Napa Valley. They traded it for seashell beads from the coastal tribes. They traded it for salt from the South Bay tribes. They had a nice thing going on. Then the Americans showed up. Actually, the Spanish showed up and removed all the tribes from their land. And all it was after that was cattle ranching. So I'm not going to show that part. It was just nothing but an open cattle ranch. The Americans showed up, they chased out the Mexicans by legal and extra legal means. And they discovered all these resources. First one they cut down was the redwoods. There was a redwood rush in the 1840s, and they were all gone by 1860. They were entirely gone. There's a single old growth, one single old growth redwood left. And later on, they dug out all the ochre too, because it was good for making red paint. But the big resources were stone and water. Water, and I'll get into that. But here's where the towns. And when they wanted to develop, first thing they needed was stone, because you want to build wharves along the coast. You want to build foundations for buildings. You want to build railroads. And stone was necessary for all that. And now, I'll show that a little later. They used it up. And of course, water, there were water wells. There was abundant groundwater along here. And when they dug out all the ochre, they discovered there was a huge deposit of pyrite underneath it. And they mined that out too. So I divide Oakland's history into two periods from 1850 to 1906, because the San Francisco earthquake happened then, and a flood of displaced people showed up and created a burst of development in Oakland, and everything changed. And this is what's happened. This all got developed into residential areas, industrial areas, landfill areas. So take a look at that while I refresh my throat here. All the old, all the old that I want to do there. I think I show it later. You'll see this whole block, which is now a very upper class neighborhood, is covered with rock quarries. So that's Oakland's landscape and a bit of the human relationship with the landscape. I'm going to get into the bedrock too. And that's that other long sentence I recited to you at the beginning. And it's all about a subduction zone to begin with. And you're familiar with this. This is the kind of place where you live right now. You live in the beautiful classic subduction zone. Only instead of the Sierra Arc, we've got the Cascades Arc and so on. But this is the California version as it used to be. And as you see, and as I referred to in the beginning, there's a great diversity of rock types in here. And to begin with, we have the accretionary wedge. That's the stuff that just piles up against in the trench against the continent. And it's represented in Oakland by the Piedmont Block, which, as I said, is the same kind of rock underlying the entire East Bay. And its cool rock type is melange. It's a mixture of, and it's preserved in Oakland's Mountain View Cemetery, which is made the subject of chapter 4. It consists of blocks like these radiolarian cherts from way out on the deep sea in a matrix of mostly sandstone and shale. And it's also got high grade blocks in it, like this wonderful blue schist. And it's even got what I interpret as classic eclogite. You know, you've got your garnet, you've got your sodic amphibole and what looks like, and this is your sodic amphibole, this is your omphacite and your that's the name I'm spacing on, glaucophane. So this is your classic glaucophane schist. Here's that, and this is what the block was good for. It was good for crushed rock. All these quarries produced crushed stone to build a major city. And every one of them is closed now. This was the last one, the southernmost one, closed in 2003. So that's the accretionary wedge, and we're lucky to have a piece of ophiolite too. That's this part, a chunk of seafloor crust marooned on land. And these are actually, it's not a very good ophiolite, but it's the one we have, the Coast Range ophiolite. And it's been thoroughly dissected. There are 3 pieces of it here, which are unconnected with each other. One is a big body of serpentinite in the hills. And serpentine is gorgeous stuff. I don't know if you have any up there in Portland. It happens when mantle rock is infused with seawater at depth, and it transforms it to serpentine minerals and expands the rock by about 10%. So it's a very disruptive process. And and then there's also this is metavolcanic clastics. This is seafloor ash that has gone through a lot of changes in the subduction zone. This is interesting in Oakland's history because it's full of pyrite. And so as it weathers, it gets this lovely thrust of iron oxides. And that's where the ochre deposit came from. And that's why underneath it has all this pyrite. This is actually what ore geologists call a gossan. This is an iron cap on top of the underlying pyrite load. And when it was all mined out and when the ground was disturbed, all that pyrite has created acid mine drainage. So Oakland not only has all this Western style stuff, it has Eastern style acid mine drainage too. And then the third part of the ophiolite is this body of gabbro, bits of which are in Oakland. And that's beautiful stuff too. Gabbro is basically a granitoid with nothing but plagioclase and dark minerals. So moving past the subduction complex, sorry, we have the last part, the foreland basin. That is this part, the part that corresponds to where you all live. You're living in a foreland basin. And that's all this the green stuff from the traditional map colors for the Cretaceous, specifically the last late Cretaceous, the Campanian, and a bit of Eocene too, called the Great Valley Sequence. This is your basic sandstone, and this sandstone, the Redwood Canyon Formation, actually yielded real dimension stone, but because all of our rocks are so shattered by the Hayward Fault, it caused some vexatious difficulties in acquiring enough good stone to build the Unitarian Church back in the 1890s. So this is the only building in Oakland made with native building stone. And the rest is, we've got some conglomerate and we got sandstone and shale, and that's all there is to say about that. The foreland basin sediments, that's everything else in this map, all the way out to the end. They result from the change from a convergent regime to a transcurrent regime. And with that change, a little window behind the descending plate opened up to the mantle. And that's what we refer to, locals call a slab window. And so this fresh magmas came pooching up over the years. And that accounts for this part. These are volcanics. The rest are all clastics. And they, going from old to new, we've got mudstone, we've got diatomaceous chert, as opposed to radiolarian chert. This is part of the classic, the giant chert beds that yield California's oil. And we have more conglomerate, young conglomerate. We have, here's your volcanics, nice andesite with beautiful amygdals in it, up in the hills of the Moraga Formation. And at the same time, there's freshwater limestones in between the lava flows. And then finally, we've got a proper basalt, the Bald Peak basalt, about 9 million years old on top. This is the youngest rock of them all. And the hills are preserved in beautiful open parks. This is part of Sibley Volcanic Reserve Regional Park. It's an old quarry, so it's all quarry pits with beautiful exposures and popular human constructions too. So, come to Oakland and see some of this stuff. And so that's where I get off saying we have more kinds of rocks than any other city in America, and geology in general. So I just want to say a couple of 1 minute at the end of my talk. Deep Oakland was a very successful book. And I say that because I just learned that 90% of all books that are ever published in the United States sell less than 1,000 copies. And Deep Oakland has sold around 4,000 so far in the year since it was published. It's been a year since the 2nd of May. That's when it's published. And it's been very gratifying. And I want to say that because Portland, too, is a deep city. There is a deep Portland out there. There is a book. There is a deep Portland book. And one of you guys could very well be writing it. You know, you guys are experts. You've lived there. You've seen it. You've visited all over the place. You know, think about it. You've got some good local regional publishers who would be interested in doing that. So think about that. Thanks.
Andrew, what a wonderful story. And I had absolutely no idea that, because I'm always striving to get all the rock types to show, because I live in Central Oregon, all volcanic, right? And all you have to do is go, okay, kids, let's go look at this and this and this, and you can see all of them. How cool is that?
It is. And, you know, over the years, I'll be posting something and people will comment. They'll say, oh yeah, I grew up in Oakland and I'm a geologist today. I'm going, you got it. You know, good land produces good geologists.
Oh my gosh. So we did get some questions.
Okay.
And starting with, during an earthquake, will places with the clay base experience liquefaction? And I think this came through, Alice, you can clarify here, but I think this came through when you were talking about some of the older terraces.
Yeah, yeah, I did mention that. It like I showed you, it's very, very firm. And likewise, the dune sand is very, very firm. And it's as thick as 60 feet. Now, liquefaction is a risk with very shallow aquifers, you know, gravel beds that are full of water that can be easily mobilized during shaking. And maybe you've heard during Loma Prieta that there was a major freeway running through this part of town, just north of the dunes and in artificial fill. And that's what liquefied. The rest of the city came through beautifully. And as I showed you in 1868, it also survived well. So I reassure people that liquefaction, you know, there's some risk here in your alluvial fan and certainly down in the artificial fill zones. But in these particular quaternary landforms, it's good ground.
Oh, that's good to know. Olive, wow, that's a wild transformation of Lake Merritt from a big estuary to a small lake. Is that mostly due to human activity?
It is not, you know, like I said, well, actually, I can say something about it. It's if you look at the 1857 map, and if you compare it to today, well, some of it's been filled in, this part's been filled in, and the whole thing, this all has been filled in. There's just a tiny little tidal channel going there. All this has been dredged out and filled in, you know. So, and it's got stone walls all the way around it, except for that little bit where I showed you where I showed you this stuff. So anyway, the next question, please. I guess we have a lot of them.
Okay, sliding down here. Oh, Carol pointed out Deep Oakland, you mentioned it earlier, Andrew, is also available on Kindle.
Yes.
So yeah.
Yeah, it's and it's for half the price, takes up no space. And as a bonus, all of the links in the end notes, I use a lot of URLs in the end notes. They're all live. You can just click them. So that's a real convenience. I have a copy myself.
Well, and this is a comment, and I totally agree with Alyssa. that she said, I love seeing the ecological connection to the geology. The different plants like different soils. And I also appreciated the human contact from Native American through the landscape changes. And as having worked with mineral material for most of my career, I certainly appreciate restoration of quarry land. And I was, you got that lovely cemetery, and I'm sure that that was a quarry prior to becoming a bit of a cemetery. And just seeing
It very well could have been. It was good rock, but the city fathers got a good deal on the land out there. They said, for world-class city needs a world-class cemetery. And there's some very prominent Californians buried there because that was the place to be, the place to formerly be, The other quarries, there's parks, there's a church, there's a tennis stadium, the book goes into that. And so there's a whole presentation about that.
Well, I think that's a wonderful use of our landscape. Andrew, this has been absolutely delightful. And Paul, thank you. Paul Shia, thank you so much for connecting us with Andrew, because wow, woohoo.